Hello, everyone. This is Humayun Aryan. Thank you for joining. Welcome. Before we get to today's speaker, we have an announcement, and Mathew Argyle is here to tell us about that announcement. And we will get started after that. Thank you. Matt, please.
Hi, thank you. My name is Mathew Argyle, and I'm part of Machine Learning Exploratory Committee for NFSF's Shine, GEM, and CEDAR communities. And next week we have a presentation about ethics and interpretability in AI. And we're trying to get community input on sort of guiding policy and what the community thinks about ethics in AI, and have a form that we would like people to fill out to provide their input. So I'm putting that into the chat now. And if you have time and would like to answer the two questions, we'll present the results at next week's seminar.
Thank you, Matt. Back to today's speaker. It's a great pleasure to introduce Professor Mathew Owens from the University of Reading. Professor Owens received his PhD in 2003 from the Imperial College London. He has been working at the University of Reading since 2010 at the Department of Meteorology. Professor Owens is also visiting lecturer at the Department of Physics, Imperial College London. He is a co-investigator for the Solar Orbiter Magnetometer instrument. He served as an associate editor for AGU's Journal of Geophysical Research, The Space, between 2011 and 2014. He is primarily interested in the solar wind, the heliospheric magnetic field, and coronal mass ejections, and the intrinsic link between them all. This spans a range of time scales from the minute of a space weather to the millennia of long-term solar variability. He is interested in empirical and numerical space weather forecasting and reconnections of long-term solar variability. Today, he will be discussing extreme space weather and the solar cycle. As always, I would like to remind you that this presentation is recorded, so please keep your microphones muted. If you have any questions, please post them in the chat box, and we will get to the questions at the end of the talk. Professor Owens, thank you for accepting our invitation. Please go ahead when you're ready.
Many thanks for that introduction. So today I'm going to talk to you about extreme space weather and the solar cycle. This is work done in quite close collaboration with Mike Lockwood and Luke Bernard at the University of Reading and many other people. And there's been a lot of work recently. I think Jeffrey Love spoke recently in the seminar series about extreme space weather, and there's a lot of interest in how big an extreme event can get. This is a different question that I want to broach today, and that's, is there any predictability in when these extreme events will occur? So rather than looking at magnitude, I'm looking at timing. So the talk's kind of split into two halves. The first bit is a bit sort of tutorially, lots of background material about how we know about space weather and space climate in the past. And then the second half is more on the focused research question of is there any predictability in the timing of extreme events? So hopefully I can, there we go. So this is the first half, the tutorial bit. So I'm going to look at reconstructing, when I say space weather, I'm going to look at the near-Earth solar wind conditions. And the reason for that is that we have different proxy data, and that's the one thing we can reproduce from all of the different available proxies. So I'm going to start with spacecraft data, and for the last 50 years or so, we have good observations of the in situ observations of the solar wind conditions in near Earth space. So those are an excellent observational data set, but 50 years isn't very long. If you're talking where a cycle is 11 years, that's only 4.5 cycles. So we need more indirect information, and geomagnetic observations can take us back about 160 years, which is a great data set, and I'll be using that in detail. But again, in terms of putting together a climatology, it's not great. We do have the sunspot record, which takes us back about 400 years. And so you've probably all seen Galileo's little flipbook animation here. I don't think he made the GIF himself. That's something someone else has put together. But the real wealth of data that we have going back into the distant past comes from what are called cosmogenic radionuclides. I'll explain that term. And that's how we can use tree trunks and ice cores to tell us about solar activity in the past. So I'm going to work through each of these in turn, starting with the spacecraft data. And what I'm showing here are two particular measurements that are of particular interest for driving magnetospheric activity. The top panel, hopefully you can see my mouse pointer, the top panel shows the field magnitude in near-Earth space carried by the solar wind over time. The white line is a 27-day average and the red line is a 1-year average. And then in the background, the black shaded region is the sunspot number, just to show you where we are in the solar cycle. And so you can see that the field magnitude goes up and down with the solar cycle most of the time, and that the field magnitude has been slightly declining the last 3 cycles. I've got an updated plot in a minute with the most recent one. So that's the magnetic field intensity. On the bottom panel is the solar wind speed. And fast wind is typically 750 kilometers a second, and slow solar wind is typically 300 to 400 kilometers a second. And so that's what defines the limits of this axis here. But you can see when we take these long averages, 27 days in white, 1 year in red, there's very little variability actually in the solar wind speed we encounter at Earth on those long time averages. And that's because it's a very local measurement of the slow wind band that the Earth typically sits in and only dips in and out of occasionally. But in terms of reconstructing properties in the past, it's difficult to reconstruct those two properties directly. And what we can do instead is a more global property. So those are point measurements in near Earth space. What we can reconstruct globally is something called the open solar flux. And just to show an idea of that, here's a little cartoon on the left. We've got the sun, and then I've drawn on a yellow surface there. That is a completely hypothetical surface that I'm going to call the source surface. Any magnetic field that gets up to that height, I'm going to say is dragged out by the solar wind, because you can't have a perfect dipole with an expanding atmosphere. And so you can see that these gray lines here would all contribute to the magnetic field in the heliosphere because they'd be dragged out by the solar wind, whereas these black loops inside would not. And this is a global measurement, a global property, but we can estimate it from in situ measurements, because if we measure the radial field at any point in the heliosphere, if we assume that that radial field is roughly constant over all latitudes and longitudes, which is a big assumption, but there are a range of observations that suggest it's valid, which I don't have time to go into today. It's going to be a bit of a buzz term. If we integrate over latitude and longitude, we can use the local radial field measurement to estimate the open solar flux. And that's what's shown here. So this is the open solar flux, or the heliospheric flux, over time. And if you remember back to that plot of the magnetic field intensity in near Earth space against time, it's very similar. So the open solar flux also kind of goes up and down with the solar cycle and has been declining the last 3 minima or so by about 30% overall. And as I say, I'm introducing open solar flux not because it's of direct interest to geomagnetic activity, but because it is a property that we can get out of the other proxy data. So to go to the next best data source, if you like, this is geomagnetic variations. And I apologize for showing this movie to a magnetospheric community, because this is a really old simulation from the LFM magnetospheric model, but that's not important. All I want to say here is that you can see that the Earth's magnetic field in gray is being disturbed as a result of the solar wind driving. And so in principle, you can use geomagnetic activity as a way to infer what's going on in the solar wind. And so what measurements of geomagnetic activity do we have? Well, there are a range of ways of characterizing geomagnetic activity. The one that gets used a lot for these long-term studies is the AA index. This is a range index, so you look at the maximum and minimum disturbance in a 3-hour window. This actually uses data from 2 stations, one in the UK, one in Australia. There are no one station was operating for the whole 160-year period, so there have been station changes, but those station changes have been calibrated to a reference station, and that's the original AA index. There's been some updates to that recently that I'll talk about in a second. Of course, an index like that isn't directly telling us about the solar wind conditions, and so I realized that solar wind coupling function, I know Steve Milan talked recently, and that solar wind coupling functions can be something of a flashpoint at times. There are many different options here, and a lot of work done in this area. I'm just showing one here for illustration more than anything. So this is the Vassalunas scaling function. And the idea here is that the power input to the magnetosphere scales with some power to the solar wind density, some power to the field intensity, some power to the solar wind speed, and then there's a term here, sine forth theta over 2, which is to do with the magnetic field angle. And there's a free parameter in this, and empirically we find it's around 0.3 to 0.4. And so what that means is that it scales weakly with the density, it scales fairly strongly with the field intensity, and it scales very strongly with the solar wind speed. Now, the big controlling factor, of course, is the field direction. When the magnetic field is southward, you get high power input to the magnetosphere. When the field is northward, then you get low power input. So it acts as a bit of a half-wave rectifier. Now, the south-north component in the solar wind is a rapidly varying component. And so in order to relate geomagnetic activity to solar wind conditions, we typically look over long time periods where this field angle averages out. And so we tend to look only at annual variations. So you can already see the problem for space weather here. But here's just 2 different activity measures. I'm not going to go into detail about what they are. This is something based upon the AA data set, and then there's a median index. But all I want to show here is that for annual means of these different geomagnetic activity measures, they scale differently with solar wind parameters. So the AA index scales with BV squared, and you get a very good linear correlation out of that. Whereas the median index scales with BV up to the approximately 1/3, and again, a very strong correlation and very linear. So that means if we have both of these measures, we can isolate the magnetic field and the speed contributions. And so we can individually reconstruct magnetic field intensity and speed by having these indices that have different dependencies on the solar wind inputs. And so this is the kind of reconstruction you get out. This was some work done by Mike Lockwood. Sunspot number is on the top panel to show you where you are in the solar cycle. Then in the second panel, it's labeled B here, we've got reconstructions of the magnetic field intensity in the solar wind, and the blue are the spacecraft observations. So you can see the agreement is really strong, very, very high correlations, highly significant. Then we have the solar wind speed. This is a very compressed axis here, so you can see the variation, but again, a very good correlation. And if we combine the speed and the field, we can work out the radial component of the magnetic field. So just using a Parker spiral model for the solar wind, if you like, we can then compute the radial field and what the equivalent open solar flux would be, which is shown in the bottom. And so again, it moves very close to the magnetic field intensity, and it agrees very well with the field observations. And so that gives us 160-ish years of reconstructed solar wind conditions at the annual timescale. So that's a really useful data set. But we want to go back further than that, as I say. And so next we have to go to sunspots. This is a controversial topic, if you like, in the solar community, how you put together sunspot observations that span a very long time period, because we start with these amazing sketches. I was going to call them crude, but they're absolutely amazing, from Galileo. These are from 1611, shortly after he put together his telescope. And then we have more modern times, of course, his kind of Eye of Sauron image from the Swedish optical telescope of a single sunspot. And so you can immediately see the problem here. You want a consistent record of solar activity over this long time period, but the ability to measure sunspots has come on a little bit in that time. So you need to be very careful that you're not getting a trend in the number of sunspots that simply comes from increased ability to detect sunspots. And that's where the controversy is how do you put, obviously we don't have one observer for the 400-year period. In fact, even for a given observer, their eyesight tends to decrease over time. And so you can't, calibrating together different observers is difficult, but even for a given observer, they have a visual acuity that declines with time. And so how do you calibrate those against each other and put together a consistent series? And that's something I don't want to get involved with today, but just to say, here are some example records. So this is group sunspot number, the idea being that individual spots with the early telescopes were quite difficult to see, whereas sunspot groups are bigger objects or features on the sun. And so a group sunspot record should be more consistent with time. The original record that was put together was by Hoyt and Shatton in '98, and that's shown as a blue dashed line on here. The general consensus is that it sort of underestimated activity in the early period and overestimated it in the late period, so you get too much of a trend. A more recent calibration was put together by Svalgaard and Shatton. I think this is a lot closer to the truth, is my gut feeling, but it may have reduced the trend too much. Whereas an intermediate series that uses a different way of joining the different data sets together was put together by Ilya Ososkin, and that sort of sits halfway between the two. But regardless of the differences between those series, they show a lot of similar trends. And one is that activity sort of increased through most of the 20th century, but has been declining recently. There was a period of very low activity around 1800 that we call the Dalton minimum, and that the most notable feature here is this Maunder minimum period around 1650 to 1700. And that isn't an absence of observations. There are actually a lot of people looking for sunspots, a lot of competent observers in this time. There just were very few sunspots on the sun at that time. So that's a real period of interest if you want to understand space climate, because it's different to anything in the rest of the record. Of course, sunspot number or group number is not a physical measure of anything. It's just counting spots on the sun, and you've got some arbitrary threshold for what is and isn't a spot. So how do we go from that measure into something physical? And I'm not going to go into the details here because this is another entire seminar unto itself, but because open solar flux is a conserved quantity, we can model it as the rate of change of open solar flux as just the difference between a source of open solar flux and a loss of open solar flux. And we know very well that new open solar flux, you've got to take a loop from below that source surface and drag it through. And we know that that process is carried out by coronal mass ejections. And so we know that the source term is related to the rate of coronal mass ejections, and we know that's related to sunspot number. So we can characterize this source term in terms of sunspot number. And it turns out that we can do something similar for the loss rate. The loss rate varies with the solar cycle in a repeatable way. I'm really sweeping the details under the rug here, but I just want to get to the conclusion that is we can model open solar flux using just sunspot number. I'll just show you the results for that instead of going into the theory behind it. This is open solar flux against time, and apologies, there are two different time axes here. This is 1600 to roughly now. The red and the blue here are different sunspot records. The black is the geomagnetic record, and the agreement is pretty good. If we do a more detailed analysis accounting for uncertainties in the sunspot records and converting it to field intensity rather than open solar flux, again, the black here is the geomagnetic record. The green is the sunspot record and its uncertainty. And you can see, again, the agreement's very good. And so we have the idea that we can reconstruct solar wind properties just from sunspot record. Apparently, sounds in the, apologies if you can hear that, sounds like my kids are very excited by space physics. I can assure you they're playing a game. They're very unexcited by space physics. To go back further in time, I need to introduce a bit of particle physics. So there are cosmic rays striking the Earth's atmosphere all the time. These are relativistic particles moving very, very close to the speed of light, mainly protons, some heavier ions. When they arrive in the Earth's atmosphere, they interact or spallate with atmospheric molecules, and they produce a shower of exotic secondary particles, pions and muons and gamma rays and all that stuff that costs a fortune to generate at CERN is happening above your head all the time. One of the decay products from all those exotic particles is energetic neutrons. And so those arrive down at ground level and we can detect them. And here is one of the longest records. This is from the Oulu neutron monitor in Finland. And you can see that there is, so the gray and white again are alternate solar cycles. You can see that there is a roughly 11-year variation in this neutron record. And that is because cosmic rays are charged particles, the stronger the sun's magnetic field, the fewer cosmic rays will arrive at Earth. And so by measuring the neutron rate at the ground, we can figure out how strong the sun's magnetic field is. Now, this is only going back to the 1960s, and so doesn't do much for us in terms of space climate, but there are non-human records of cosmic ray intensity. And so this is where it really starts to get interesting. So cosmic rays are arriving at the Earth's top of the Earth's atmosphere. About 2/3 of them, excuse me, get stopped in the stratosphere, which my meteorological colleagues assure me is very dry and boring, whereas about 1/3 of them get down to the troposphere, which is both damp and exciting, I'm told. Now, the cosmic rays, when they interact with molecules in the Earth's atmosphere, one of the decay products is carbon-14. That's not naturally occurring in the Earth's atmosphere. You probably have all heard of it because that's how we date organic matter, and we do so because it is produced by cosmic rays. It has a half-life of about 5,000 years and it has a production rate that is reasonably high, at least compared to the other isotope of interest, which is beryllium-10. It has a half-life of about 1.5 million years and a production rate that's a couple of orders of magnitude lower than carbon-14. Now, beryllium-10 attaches itself to aerosols and then gets precipitated out. So it falls out either as ice or snow. Most of it falls over the oceans and so is lost and is no use to us. Some of it falls as snow over ice sheets. And so year on year, you get layers of compacted ice. And if the further you drill down into that compacted ice, the further back in time you're looking. Now, because the stratosphere is so dry and boring, it takes about a year to get it out of the stratosphere, whereas it takes about a week to get it out of the troposphere. And so if you change your top of the atmosphere cosmic ray intensity, you're smearing out your signature in the ice sheets by about a year. And so the highest resolution you can look at for solar activity is about a year in beryllium-10. Carbon-14 is even worse because it gets locked up in the carbon cycle. The oceans are involved in the carbon cycle, which means that they have very long time constants, anything between 20 and 50 years for ocean overturning. It gets eventually locked up in biomass, and so tree trunks and corals and things like that are a source of cosmic ray records back in time through carbon-14. That means typically, and this is changing rapidly, techniques are coming on very rapidly in carbon-14, but historically we've not looked at individual solar cycles in carbon-14. But as I say, that's starting to change now. The important thing here is that these deposition mechanisms are completely different. If you have a change in Earth's climate, it will change the carbon cycle, and it will change the local precipitation rate, but it won't do so in the same manner. And so when you see common signals in your beryllium-10 and your carbon-14 records, you can be pretty confident it's because the cosmic ray intensity has changed. And so by looking at carbon-14 and beryllium-10 records in ice cores and in ancient trees, we can figure out what the cosmic ray intensity was back in time, which tells us how much open solar flux there was back in time. So what the cosmic ray community tends to talk about is the heliospheric modulation parameter. That just says how good is the sun at stopping cosmic rays reaching Earth. So the better it is, the stronger the sun's magnetic field. So the higher up on this y-axis here, the stronger the sun's field. This is a 10,000-year record from a variety of tree trunks. What looks just like spiky noise is actually is signal. This is the Maunder minimum shown in the pink shaded area. This is the space age shown in the green shaded area. So I'll put that in a bit of context here. So this is my sort of summary movie, if you like, for solar wind reconstructions. It's field intensity in near Earth space. So this will be very closely related to geomagnetic activity. And this is time along the x-axis. And so this is 1 minute data from spacecraft, actually from the WIND spacecraft. And this is about 12 hours worth of data. And what I'm going to do is expand the time axis and then sample the data down a bit, just because it would get too spiky otherwise. And so we've got minute data there. We can see a CIR. This is now hourly data. And then we're going to daily data. And you're starting to see the solar cycle emerge now as we sample down to yearly data. So there's the entirety of the space age with the 4.5 cycles. Then bring in the geomagnetic data, which takes us back to 1860. And then bring in the sunspot data, which will take us back through the Maunder minimum to 1600. And then downsample to about 20 years resolution and bring in the cosmic ray data and spin it all the way back 10,000 years or so. So I could happily talk about this movie for another hour or so, but I won't. I want to say a couple of key points, though. The first is that if you want to put together a climatology of space weather, using spacecraft data is not going to get you there, because the spacecraft data is 2 points up here. They're both together up here on the graph. So it clearly doesn't span the range of variability that the sun can exhibit. The geomagnetic data takes us back a bit further and drops down to about here, but still is not spanning the full range of variability, just something to bear in mind. The sunspot record is useful, despite it being a very indirect proxy for solar activity. It comes down here to this Maunder minimum period, and so pretty much spans the full range of variability over the 10,000 years of the cosmic rays. So just to show that in a bit more detail, There's the cosmic ray record. Zooming in just on the last 400-year period here, you see the agreement between the cosmic rays and the other proxies is pretty good in terms of getting a long-term trend, not resolving individual solar cycles, and then was completely messed up by the airborne nuclear tests, and so we don't have a cosmic ray record past about the 1960s. Okay, so that was the tutorial bit. Now on to the sort of more new science. And the question I want to pose is, does extreme space weather follow the solar cycle? And so are we more likely to get extreme space weather at solar maximum, or is it more random? And you might think that's a completely trivial question to answer, but I don't think it had been well answered before. Of course, we know that space weather follows the solar cycle, at least moderate space weather. This is Sabine's paper from 1850, where he looked at disturbed geomagnetic days. So he's just using a ground-based magnetometer, obviously. He looked at the total number of disturbed observations. I think there were approximately hourly observations. Sunspot minimum was about here, when he was getting sort of 2,000 to 3,000 disturbed observations per year. Sunspot maximum was up here somewhere, where he was getting closer to 7,000 to 8,000 disturbed observations per year. So it was pretty obvious that moderate space weather, at least, is following the solar cycle. And you can look at that with other indices too. This is the AP index, doesn't really matter. But here are annual averages of AP, so space climate. And then shown here, I've just taken a threshold taken the whole AP data set, applied a threshold to find the top 5%, and so it's about 39 nanotesla, and then looked at the number of days per year that exceed that threshold. And so that's shown down here. So this is effectively storm days, if you like, for a very low intensity definition of what is a storm, the top 5% of observations. And you can see a close correlation between the annual averages and the number of storm days. Here's the correlation down here. So clearly space weather is following the solar cycle, but it's unclear whether that applies for extreme space weather, where I'm talking about 1 in 30-year events, maybe 1 in 100-year events. The problem is that they're rare, and so we don't have good statistical data for them. There's also a lot of talk, I think it's fair to say, in the solar community, that you hear the sort of anecdote that the Carrington event, so this event in 1859, that was observed by Carrington, that was just before solar maximum, and it was in a very small cycle. And so there is sort of this anecdata drawn upon analogy that extreme events don't follow the same rules as these more quiescent events. So it would be nice to say something more quantitative, because if extreme events do follow the solar cycle, then that's a useful thing to know in terms of planning. So we need long records. And so most of these studies, the previous studies have looked at the AA index. Amelia Kopua has a really nice study from 2015. This is a figure from her study. So this is the AA index as a function of time. This is sunspot number as a function of time, so you can see the solar cycle. And then the red dashed lines on here are the top 17 storms. So that's just under a 1 in 10-year event. So moderately extreme, can be moderately extreme. And maybe you would say there is some clustering about solar maximum, but just by looking at that plot, it's not clear whether that's purely by chance or whether there is some real information in there. And she concludes, and I agree with this statement, the quieter sun can also launch superstorms. And there was a similar study by Wennerstrom. The conclusion there was that stronger cycles give you more storms, but the pattern's not very clear because large storms are relatively rare. I agree with that statement too. But what I want to know is the likelihood of an extreme storm more likely at solar maximum, and is it more likely in a big solar cycle? So those are the two things I'm going to try and be a bit more quantitative about. So this is the data that goes into it. I've got sunspot number on the top with white and dark being alternate cycles. And then this is the sort of important panel, if you like, in the middle. This is the AAH index over the last 160-ish years. This is AA, but taking account of the fact that the Earth's magnetic poles have moved quite a bit during that period. And if you don't correct for that, you get systematic trends in AA that are not representative of changes from the sun. And so this is a data set that Mike put together that takes account of that. And what I've done, that's a 3-hour index. What I've done is take daily values because storms are typically of order a day. And then in the bottom here, this is the number of storm days per year, effectively, for different thresholds. And so if I use a very low threshold, the 90th percentile of the AA index, that's shown in blue, and you can probably see by eye, there's a clear solar cycle variation. Whereas if I take a very high threshold, the 99.99 percentile, I only get 6 events. They're shown in red, and it's not clear to me whether there's any information about them clustering around solar maximum, or whether they are more likely during big cycles. And so I need some probability models to compare to say, is this occurrence by chance, or is there actual information in there? So this is just to show the variation over an average solar cycle. So I take the start of the cycle, a solar cycle, solar minimum to be phase 0. I take the end, the next solar minimum to be phase 1. And if I take an average over all the solar cycles, I get, for sunspot number, I get the nice asymmetric sinusoid. So solar maximum occurs around a solar cycle phase of about 0.4. And then I'm going to define a quiet period, which is the times in white, and an active period, which are the 2 gray shaded regions. If I look at the number of storms over a solar cycle, so just looking at panel B here, for the quiet storms, there's a bit of a weak trend. For the bigger storms, you can see that they are clustering around this active period. And the active period has been defined by when these storms are occurring, I should say. And so, but the question is, particularly for these red events, the very extreme events, is that just by chance? And so the probability models I'm going to use to test that, so I'm going to come up with a null hypothesis, which is that this extreme event occurrence is just completely random. They can occur at any time, and the fact that there's a few more at solar maximum is just a pure chance. And so in that case, my probability, so this is probability on the y-axis against time, a year, and so the blue line here is just my random model, which says storms occur at any time with equal probability. And then I've got a solar cycle or a solar phase model, which is shown in red, which says that the probability of a storm is about 6 times higher during an active phase around solar maximum than it is during a quiet phase around solar minimum. And so my probability just goes up and down with the red shaded region. So I'm going to use that to test whether there is any information about the timing of extreme events around solar maximum. And then there's some other ones too that I'm not going to go into detail here. The obvious one is the phase and amplitude one, where the probability of an extreme event is higher in the active phase, but the height of that probability is proportional to the magnitude of the solar cycle. And so you get a high probability in 1960 when we had the biggest solar cycle we've seen. You get a low probability around the turn of the century when we had the smallest cycles we'd seen. So that's what I'm going to use to test the observed trends. And this is the first result. It takes a bit of talking through, so just bear with me. Top here is the probability distribution. So essentially just number of events against storm threshold. And this is during the quiet phase. So at solar minimum, we do get lots of small storms, but the number of extreme storms, if you follow the black circles, drops off very rapidly. Whereas during the active phase, that's the middle panel, the probability drops off far more slowly with storm intensity. We do get more extreme storms during the active phase. Now, the question is that just by chance? And so what I've done is taken the random model where storms occur at any time is shown in blue, and I sampled from that 10,000 times, and I sampled the number of events that's equal to the number of observed events. And so you can see that during the quiet phase, if I have storms randomly occurring at any old time, I massively overestimate the probability of extreme events. Whereas it's during the active phase, I underestimate the probability of extreme events. And this in the bottom is the difference between of event occurrence between active and quiet phase. And so, of course, for the random model, there is no difference. And so the probability is 0 at all times. Whereas for the phase model, it agrees very, very well. There is some overestimate down here for low thresholds. And I think what's going on there is we're getting CIR-driven storms at very low thresholds. Once we get up to about the 99th percentile, these are mainly CME-driven storms, and this idea that the number of storms increases around the active phase then holds very strongly. And so whether you follow that or not, the conclusion here is that the probability of extreme events follows the solar cycle for all the thresholds that we are able to look at with the AA dataset, which is up to about the 1 in 30 year event. So we can conclude that even though we've only got 6 events at this highest threshold, we can dismiss the null hypothesis that they're just occurring randomly with time. The second question I wanted to address was, do you get more storms in big cycles? And so what I've looked at is the correlation between the cycle magnitude and the number of storms. And I've done that for increasing threshold. And so you see around that 99th percentile again, you get an almost perfect correlation between the number of storms and the cycle magnitude. But as you go to higher thresholds, and this was what the Venestrom and the Kilpua studies concluded, as you get to higher and higher thresholds, that correlation drops off, and you can't obviously conclude that you get more extreme events during big cycles. But of course, if you've got fewer events, correlations drop. And what we find by sampling from our probability models is that the red line here has a perfect correlation between number of storms and cycle magnitude. And the correlation, if there is the correlation coefficient, if there is a perfect underlying correlation, just because the number of event drop-offs is exactly as we observe. And so whilst we can't dismiss the idea of there being no relation at the 95% confidence level up at these high thresholds, I think the data are saying that the most likely conclusion here is that the probability of extreme storms increases with cycle magnitude. In fact, when we get to that very highest threshold, and you can see the effect of 1 or 2 events here. So, statistically, we're on a bit shaky ground, but we can dismiss that null hypothesis that there's no correlation between cycle magnitude and extreme storms. One last rule I wanted to introduce, and I'm not going to show you the data because it gets a bit complex here, but what we found is that there's a difference between odd and even cycles for the very extreme events. So for the moderate events, they are distributed within that active phase around solar maximum approximately uniformly. But when we get to the very highest events, during odd cycles, such as the coming cycle, or the cycle we've just started, cycle 25, we find that extreme events tend to cluster just after solar maximum, whereas during even cycles, such as cycle 24 that we've just left, those extreme events tend to cluster early in the cycle. And we think this is related to the overlying field of the sun. So for small storms, it doesn't matter. What matters is this intrinsic magnetic field inside the CME. But to get to the very extreme events, you need perfect storm conditions. And we think they're dragging out the overlying magnetic field of the sun, which tends to be southward during those periods I just mentioned. And that's giving us enhanced geomagnetic activity at those times. Now, of course, the test is all well and good mining a data set and finding some trends, but what you need is independent validation that isn't in your training data set, as the machine learning folk will tell you. And so we've been quite fortunate in that there are two very well-known events that aren't in the AA data set. The first is the Carrington event, 1859, that's pre the AA data set. And then there's the July 2012 event that went over stereo A, because it wasn't Earth directed, is not in the AA dataset. So both of those events were fairly close to solar maximum. They're both in even cycles, and they both occurred just before solar maximum, as we would expect. So, I mean, two independent verifications is not much, but it's good that those most extreme events that we have in the quasi-recent period do seem to work out. Going back to that cosmogenic record, which I've neglected a bit for a bit of this talk, I said that the carbon-14 record tends to look at very long time period variations, and it's difficult to resolve individual solar cycles. If you look at one period in a lot of detail, you can start to tease out individual solar cycles. And if you smack the magnetosphere with enough radiation, you can produce a big enough spike in carbon-14 production that you can see individual solar space weather events. And there are three particularly well-known events that have been studied recently. There's one in 994 AD, one in 1052 AD, and one in 1279 AD. And they're shown as the red arrows here. And those all occurred pretty close to solar maximum. So the other big space weather events that we know about that aren't in our AA dataset also appear to have occurred during what we would call an active period. Unfortunately, we can't work out whether they're during even and odd cycles because we can't consistently count cycles that far back. The data just aren't good enough. So just finally, putting it all together, can we use this to make any kind of useful prediction? Well, the problem is that solar cycle prediction is not quite the science we would like. Not that there's not lots of good work going on in this area, but we still don't know how big solar cycle will be. So what I've done here is to just look at three scenarios. And I've taken the last 100 years of data and pulled out the kind of Goldilocks events, if you like. The average event is solar cycle 23, which is shown as a black dash line here. And then the biggest event is shown in blue is cycle 19 in the 1960s. And the smallest event is cycle 12 around the turn of the 19th, 20th century. No, 18th, 19th century. So if I take those three events and propagate them forward, this is the kind, if I look at a moderate event threshold, I get these kind of probabilities of an event. So they ramp up during the active phase and they ramp down during the quiet phase, and they occur at slightly different times because the length of these cycles are different. If I look at the most extreme events, then my probability really changes because of that odd even cycle behavior. And I predict a far greater probability of extreme events just after solar maximum. Of course, you'll see that the probability never goes to zero. There is still a finite probability of an extreme event at solar minimum. So I've talked myself a bit hoarse, but my takeaway points, if you like, is that we can construct space weather and climate from a range of proxy data. Cosmogenic Isotopes can take us back about 10,000 years. Can't go back before that very well because of changes to the climate system during the Ice Age. But the sunspot record is really useful because it covers the full variability during the last 10,000 years. Space weather has long been known to follow the solar cycle, but there's been quite a bit of debate about whether that really applies to extreme space weather. The problem being, of course, extreme space weather is rare, and so stats are poor. But by comparing with quantitative models, we can show that the probability of an extreme event is higher during an active phase around solar maximum than around a quiet phase at solar minimum, and that the probability of an extreme event goes up in proportion to the size of a solar cycle. So big solar cycles are more likely to give us extreme events. And then we have this very curious thing that early in the active period, during even cycles, we're more likely to get events, and late in odd cycles, but the probability is never zero. So, you know, if we see one extreme event early in this coming cycle, then I'm technically not wrong. All right, thanks very much for listening. I hope you got something out of that.
Thank you, Matt, for the interesting presentation. That was really good, very clear. Just before we go to questions, I would like to remind the audience about a few points. First, not last, I would like to remind you that next week we will have a panel discussion focused on AL and machine learning, hosted by Shine, Jim, Cedar community. So please fill out the questionnaire that Mathew Argyle shared initially at the start of this talk. I'm going to be sharing that in the chat box again for those who haven't done it yet. Also, please be reminded that if you're joining from Europe, the time difference will be less. Remember that daylight saving ends on 31st of October, which is different to US. So please don't miss out on the next week's seminar or the discussion. Going to the questions, the first question: is it possible to use a contingency table and Fish's exact test to determine the probability of rare events, for example, extreme solar events?
In principle, yes. The probability, the problem we have is the sampling issue, and so the sort of the ethos I've taken here is that as we go to more and more extreme thresholds, can we pluck out a consistent behavior? I think if you just used a single test for one threshold, I don't know that you kind of want to leverage the information at lower thresholds. It's sort of like an extreme event statistics idea, but being applied to timing rather than magnitude. So you're hoping that some of the behavior of lower intensity events is giving you some information about the very tail of the distribution. And I think if you just did sort of a contingency table for a single threshold, you would be losing some of that information. But it should be a valid thing to do, yeah.
Okay, thank you. And Patricia wants to be reminded, does an event cycle have in or out magnetic field at the sun's North Pole?
I can never remember this. Let me, if I skip back, I think I had a sort of picture of it here. So let's see, during an odd cycle, the field goes into the northern pole. And during an even cycle, the field comes out of the northern pole. But it flips at solar maximum. So it comes out of the northern pole during the first half of an even cycle and into the northern pole during the second half of an even cycle. I think I won't say any more before I confuse myself anymore.
Okay. So the consequence of that is you're on these late odds and early evens, you're more likely to have southward IMF coming toward the Earth. In this simple model,
You're more likely to have southward field in the corona, when it gets pulled out into the heliosphere, of course, for a perfect Parker spiral, it lies completely flat. And so there is no southward field in a perfect Parker spiral. So what it requires is a big event pulling out this field whilst it's still in the corona before it's started to be dragged out, which I think is possible. But yeah, you've hit on to the key point of what we think is going on. And it's about that southward field at Earth latitude.
Okay, yeah. Thank you so much. Thank you, Patricia, for asking the question directly. Yeah, so we're almost on the top of the hour. I would like to once again thank you, Professor Mathew Owens, for accepting our invitation and for the very great talk. I also remind everybody to join us next week for the discussions, please, at a usually different time if you're in Europe. So yeah, thank you, everyone. Have a nice week. Bye.